In chapter 10, we are going to continue looking at the idea of, the electron configurations and the orbital diagrams, and we're going to be looking at Lewis dot structures. So Lewis dot structures show the valence electrons around the symbol of the element. It gives us an idea of how the atoms are connected in the molecule. It doesn't exactly tell us the 3D image of the molecule, but it gives us an idea of how everything is connected. So last time we learned the electron configuration can show us how many valence electrons are in each of the atoms. So here for oxygen, we said that the higher or the highest shell number contains the valence electron. So here it would be 2. And then shell 1 has the core electrons. So to draw a Lewis dot structure, we take the symbol of oxygen, which is just O, and then we put those 6 valence electrons as dots around the symbol. So that's kind of the gist of the Lewis dot structure. So here's some more examples. Lithium has 1 valence, beryllium has 2, boron has 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and neon 8. So we're just showing the dots around the symbol to show how many valence are in that atom. So atoms with 8 valence electrons, like neon right there, are very stable, and we call this an octet. So having those 8 valence is an octet. So the goal for atoms or ions is to lose electrons or gain electrons to get to that 8 valence, because again, it's very stable. And then for molecular compounds, they share electrons to get to the 8 valence. But the octet rule does not apply to transition metals. This only applies to main group elements. So they'll lose electrons, gain electrons, or they'll share electrons to get to the 8 valence electrons, that octet. Helium is an exception to this. There are other exceptions that we'll talk about as well. Helium is a noble gas, and all the noble gases are very stable, and helium only has 2 valence. This is called a duet. So duet is stable as well. So there are more exceptions to the octet rule, and helium is just one of them. So you're probably wondering, do I have to draw the electron configuration every time I want to figure out how many valence electrons I have? Thankfully, you don't have to do that. So all you have to do is look at what group the element is in. So sodium is in group 1, it has 1 valence. Magnesium in group 2 has 2 valence. Aluminum 3, silicon 4, phosphorus 5, sulfur 6, chlorine 7, argon 8. And that's true for everybody in those groups. Because remember, the electron configurations are similar for the groups. So they all have the same valence in those groups. But we don't use that for the transition metals, only for the main group elements. So all the A's. Okay, so I'm going to do problem 1 on your worksheet. Oops. So we have phosphorus, iodine, calcium, gallium, and argon. So looking at your periodic table, we can figure out how many valence electrons we have. So phosphorus has 5, so we would just draw 1, 2, 3, 4, 5. Sorry, that one looked more like a line than a dot. And then iodine has 7, so we can draw 1, 2, 3, 4, 5, 6, and 7. 7 dots around iodine. Calcium has 2, so we only need 2 dots. Gallium has 3. 1, 2, 3. And then argon has 8. So 1, 2, 3, 4, 5, 6, 7, 8. Sorry, some of those dots don't look like a dot. Okay, so just look at what group they're in. That's how many valence electrons they have. So we'll look at ionic compounds, but mostly we're going to stick with covalent or molecular compounds. So ionic compounds, we can show the Lewis dot structure, and I'll give you some examples here, but again, just mostly we're going to look at covalent. Okay, so let me give you a real quick example. So let's say we have potassium chloride. So potassium's in group 1, so it only has one valence. Chlorine's in group 7, so it has 7 valence. So here we know potassium's going to lose an electron, so it can become a +1 ion. Chlorine's going to gain 1 electron, so it can become a -1. So we show that the electron is being transferred from potassium to chlorine, and then we get potassium ion and chlorine ion. So now chlorine has 8 valence, a negative charge. Now they're attracted to each other. So that's how you do Lewis dot structures for ionic compounds. But again, we're mostly going to be focused on molecular compounds. So I have one more example here in your notes with magnesium chloride. So magnesium has 2 valence. And since it's MgCl2, we have 2 chlorine atoms, which both have 7 valence. So 2 of those electrons from magnesium are going to leave. One's going to go to one chlorine, the other one's going to go to the other. And then we get magnesium ion and 2 chlorine ions. So in question 2, it asks you to write MgO. Do this real quick. So we have magnesium and oxygen. So magnesium has 2 valence, oxygen has 6. So both of the electrons are going to oxygen, and we get magnesium 2+, and then 2 oxygens. Oh, I did that wrong. Not 2 oxygens, 1 oxygen, sorry. 1 oxygen with a -2 charge. And then aluminum chloride, we would have 1 aluminum and 3 chlorines. All the chlorines have 7 dots. And dots are not easy to do on this thing. There we go. So 1 chlorine gets 1 electron. So they all get 1 electron from aluminum. And then we get aluminum with a 3+ charge. And all of our chlorines have a -1 charge. Because they accepted, that electron. So they all 3 have 8 dots around them with a negative charge. Last one, rubidium and sulfur. So we have 2 rubidiums. There we go. 2 rubidiums. And they both have just 1 valence. And we have a sulfur that has 6 valence. So both of the electrons go to sulfur, and then we get rubidium ions and sulfur ion. Okay, so that's the gist of ionic bonding. That's all we'll do with the Lewis structures in ionic bonding.